Hello and welcome all. Today we are going to discuss a few topics about digital electronics. I'm Ishita Pathak, lecturer electronics from Government Polytechnic, Ghaziabad. A brief overview of what we are going to discuss in today's discussion on digital electronics. Firstly, we'll discuss about some basics about introduction to digital logics, then the gates. Proceeding forward, we will go on to universal gates, discussing what are universal gates, what are their applications. Going forward, we'll discuss about Boolean algebra, some of its laws, and how we use the Boolean laws for logic simplification questions. Then we'll go with a discussion of Carnot map, also known as K-map, and how we use the K-map rules and the basics formulas to solve again the Boolean algebra, and it is also used for Boolean simplification through K-maps. And we will end today's discussion with the topic of memories, the types of memories, and what are the specific characteristics, advantages, and disadvantages, and so on and so forth. Proceeding further, firstly, when we discuss about digital electronics, so what is a digital electronics? We need to understand what existed prior to digital electronics. So it is how we progress in technology. Analog electronics we talk of, and then we talk of digital electronics. We will compare the two of them as well. So basically, analog and digital signals are those signals which represent information differently, while analog signals are continuous and can take any value within a range. Digital signals are discrete signals, and when we say discrete, we mean in terms of the numbers. The information or the signal is represented using the binary digits, which is either 0 or 1. We see here in the slide as well analog versus digital signal. While the analog signal is seen to be a continuous signal, a continuous waveform, the digital signal is in the form of pulses, or as I mentioned earlier, discrete 0 and 1. Analog signal is a type of signal that represents continuous data using a continuous range of values. It can take a value within a certain range. Analog signals are characterized by their smooth and continuous nature, for example, a sound wave. Digital signal represents data as a sequence of discrete values using typically the binary numbers, and unlike analog signals which vary continuously over time, digital signals are discrete and quantized, meaning they can only take on specific distinct values. In digital communication and computing systems, information is encoded into digital signals for transmission, processing, and storage. These signals are commonly used in telecommunications, audio, video processing, computer networks, and many other applications. Here we come forward to discussing about the difference between analog and digital signal. So analog signal, as I said, they represent a continuous variations in magnitude over time, taking a value between a given range, whereas digital signals are discrete and quantified with specific values. The signal type in analog signal is continuous waveform, whereas in digital signals it is discrete. The processing of analog signal requires complex processing for manipulation, whereas in digital signal, it is easier to manipulate in digital terms. So, analog signals are less efficient for storage due to continuous nature, whereas in digital signal, information is stored in the form of binary numbers 0 or 1, so it is more efficient for storage because of discrete values. Typically, analog signal requires a large bandwidth, whereas digital signal requires less bandwidth for transmission. Analog audio signals, analog radio waves, human voice, etc. are the examples of analog signal, whereas digital data streams, digital audio signals are the form of examples of digital signal. One of the drawbacks of analog signal is that it is susceptible to noise and distortion, whereas digital signal is more resistant to noise and distortion. In analog signal, the circuit components required are amplifiers, filters, continuous wave oscillators, whereas in digital signal, microprocessors, binary counters, and logic gates. Signal values in analog signal has infinite range of values, whereas in digital signal it is limited to discrete values. No conversion is required in analog signal, whereas in digital signal we require ADC, which is analog to digital conversion. Analog signals are used in electric fan, landlines, radio frequency communications, whereas digital signals are used in computers, smartphones, digital sensors, digital imaging, etc. Now, the hardware consists of a few basic building blocks which are called logic gates, and the basic logic gates are AND or NOT, whereas the other gates are XOR, XNOR, and the universal gates NAND and NOR. So, the logic gates are built using transistors. A NOT gate can be implemented by a single transistor, whereas AND gate would require typically three transistors. Here we see the simple gates which are AND or NOT. So the AND gate which we can see on our right performs the function of multiplication, whereas we have two inputs A and B, and the output we will get the multiplication, which is A dot B. And this is the truth table. We can see that for a two input AND gate, while only when both inputs are 1 or logic high, we say logic high is 1, logic low is 0. So if both the inputs are high or 1, we get 1 as the output, logic high. Otherwise, in all other cases, here we can see we are getting a 0. In the next gate, the OR gate performs the function of addition. So here we can see the symbol of OR gate, two input OR gate, and this is the truth table, whereas any one of the inputs, if it is logic high or 1, at the output we get 1. Then the third gate is the NOT gate, which is also known as the inverting gate. So the NOT gate, any input that is given to a NOT gate, the output will get the inverted. For example, if we give input as 0, we get output as 1, and vice versa. If we give input as 1, we get output as 0. These functionalities of the gates can be tested and expressed by a truth table, wherein a truth table lists output for each possible input combination, as we just saw in all the three truth tables. Coming to our next topic, which is universal gates. Universal gates are NAND and NOR gates, which is nothing but NAND is a combination of AND and NOT gate, whereas NOR is a combination of OR and NOT gate. XOR implements the exclusive OR function. So universal gates are basically those logic gates which can be used to construct any other type of logic gate, which are NAND and NOR gates. By combining these gates in various ways, we can create any Boolean function, including the basic Boolean gates, which are AND, OR, and NOT gates. So on our right side, we can see this is the symbol of a NAND gate. This is a symbol of NOR gate, whereas this one is the symbol of XOR gate. In NAND gate, we can see the whatever output we get for AND gate, we put an inverting terminal ahead of it, which is the inverting gate or the NOT gate, and we get the output as the NAND gate. So in NAND gate, we can see that if any one of the input is logic high or 1, we get output as 1 and 0 otherwise. Whereas in NOR gate, if any of the input is logic 0, logic low, or 0, we get the output as 0, otherwise 1. So this is how we prove like NAND gate. How is it called universal gate? This is one of the most popular questions that we get in examinations, even in the vivas and even in job interviews, that what are universal gates and why are universal gates called so? So what are universal gates? They are NAND and NOR gates. Why are they called so? Because using these universal gates, we can construct our basic gates, which are AND, OR, and NOT. Yes. So let's see that NAND is called a universal gate, and this is an AND gate. So if we connect two AND gates in consequence, we get an AND gate. For NOT gate, we are shorting the terminal input terminal, we are giving only one as input terminal, we are shorting it, we get a NOT gate. We connect two NAND gates into another NAND gate, then we get an OR gate. So AND gate using NAND gate, for this you require two NAND gates, as you can see here. And then in the first NAND gate, the outcome is the inverse of logical AND, which we talked about in the previous slide, that if whatever output of AND gate we are getting, we put an inverting terminal, not terminal, we get an output of NAND gate. The second NAND gate that inverts this output from the first gate, thus producing the original AND gate. It is like if you say a complement of a number will be the number itself. So this is how we are proving that NAND gate is used to construct a NAND gate. So two NAND gates, one NAND gate output we got, the second NAND gate will invert the output of the first NAND gate, thus producing the original AND logic. A NAND gate is employed as a NAND gate by inverting its input and output. The outcome replicates the behavior of an AND gate, and only when both inputs are 1 does the output become 0 due to inversion, which is what we discussed in the previous slides and saw in the form of the gate diagram, the logic symbol, and the truth table. OR gate using NAND gate. Constructing OR gate involves three NAND gates, as we can see in this picture represented here. The first AND gate produces the inverse of the first input. The second NAND gate generates the inverse of the second input. And the third NAND gate computes the logical OR. OR means, we discussed, OR operation performs addition. Yes, because AND was multiplication, OR was addition. Again, one of the questions which most of the time people tend to confuse, that what is the operation. So never forget the basic functions of the gate: AND for multiplication, OR for addition. So the third NAND gate, this one here, computes the logical OR of the inputs of first NAND gate A and the other NAND gate B, and then we get the original logic truth table for the OR gate. So the NAND gate is used as an OR gate by inverting its input and the output. The result is that when both inputs are 0, the NAND gate output is 1, simulating an OR gate's behavior. Similarly, we can construct the basic gates using universal NOR gate. So for here we see in the representation, we construct a NOR gate using two NOR gates. A single NOR gate, the terminals are shorted, we get a NOT gate. And for constructing an AND gate from a NOR gate, we need three NOR gates. So the again input of first NOR gate, output of first NOR gate, output of second NOR gate is computed by the third NOR gate, and as a result we get the AND gate. Coming to the next level of our discussion, which is about logic chips. So there are integration levels, as we can see here in this slide. It is SSI, small scale integration, which was introduced in the late 1960s, and it is consisting of 1 to 10 gates. Next is the medium scale integration, MSI, which is talking of 10 to 100 gates. Next is the large scale integration, introduced in the early 1970s, and we are here talking of 100 to around 10,000 gates. And then we are talking of VLSI, which is very large scale integration, again introduced in the late 1970s. And this in VLSI, we are talking of computation or of configuration of more than 10,000 gates. So the logical functions can be expressed in several ways. We saw truth table, then we talk of logical expressions, and then we'll come to graphical form. Coming to our next topic of discussion, which is Boolean algebra. So there are a number of Boolean identities. Here we are going to discuss some of the important ones which you use to simplify your Boolean algebra questions, and how to use these identities to simplify any given Boolean simplification. Yes. So the first Boolean identity and case, we see that x dot 1 will be x, whereas in OR x plus 0 will be x. These are laws. We have to understand them. We have to learn them as it is. These are the facts. These can come from for proving as well. So there is, these are as it is. Like the sun rises in the east. Why? It is a universal fact. Boolean identities, y is x dot 1 equals to x, y is x plus 0 equals to x. These are identities. These are going to remain as the universal truths, as a universal fact. So the complement identity, next one, is x dot x bar is 0, whereas x plus x bar equals to 1. Commutative law states that x dot y equals to y dot x, whereas in our case x plus y equals to y plus x. In distribution law, x dot y plus z will be equal to xy plus xz, whereas in our version, x plus in brackets y dot z will be equals to x plus y in a bracket dot x plus z. Idempotent law says that x dot x equals to x and x plus x equals to x. The null law says that x dot 0 will be 0, whereas x plus 1 will be 1. Involution law, which says x bar and double bar will be x. So the double bar of any digit will lead to the digit itself. For example, if 0 bar is 1, but 0 double bar will be 0 itself. Yes. So the absorption law says that x dot in brackets x plus y will be x, whereas in the OR version, x plus x dot y equals to x. Associative law says that x dot in brackets y dot z equals to x dot y dot z. In OR version, it's x plus in brackets y plus z equals to in brackets x plus y plus z. Coming to one of the important laws, De Morgan's law, x dot y whole bar will be equals to x bar plus y bar, and in case of OR version, x plus y whole bar will be equals to x bar dot y bar. This is a simple logic circuit design process which involves problem specification, deriving a truth table from that, deriving a logical expression, simplifying the logical expression, and then finally deriving the final logic circuit. Deriving of logical expressions from truth tables and K-map for that matter is in the two forms, which is SOP, sum of product, and product of sums. In digital logic, SOP, sum of products, and POS, product of sums, are two canonical forms for representing Boolean expressions. SOP represents a logical sum of products, while POS represents a logical product of sum terms. SOP expresses a Boolean function as a sum, which is OR operation of product terms and operation. For example, here we see that A dot B plus A dash dot C is in SOP form. Sum of products. आपस में इनका product हो रहा है, these two, and all together इनका sum हो रहा है, which is OR operation, right? Whereas POS form, which is a product of sums, so here we see that it is a Boolean function, expresses a Boolean function as a product and operation of sum terms, which is OR operation. For example, the expression A plus B dot A dash plus C is in the POS form, where A plus B and A bar plus C are sum terms. Logic expression simplification can be done through two basic methods. One is the algebraic manipulation, wherein we use the Boolean laws we discussed a few minutes ago in the previous slides to simplify the Boolean expression, and the other method is the K-map or the Karnaugh map, which is the graphical method. So let's see, how do we discuss and how do we go for Boolean simplification using Boolean algebra? So here we are considering an example, this as a question. How do we simplify it? You can see these arrows, colored arrows. The first one is the green, orange, and the red one. So in green we are combining these terms wherein we get a common term. So for this we are talking of this and this one. Yeah. So here common terms are b plus c. In bracket we get a plus a bar, and we saw in the Boolean identities that a plus a bar is 1. So we get the simplified term for this green ones as bc. Similarly, in the orange one we see we can take common a and c, and we get in bracket b plus b bar, which is again equal to 1, so we get the term as AC. In the red one, we see we can take common AB, and in the bracket we get C plus C bar, which is again 1, so we get the simplified one as AB. So the answer to our question, which is this big, gets to this, which is what is simplification. When we talk in mathematical terms also, we get a complex equation, a big equation with a number of terms, and what we simplify, sometimes we may get 1 as an answer, 0 as an answer, or simply a as an answer. It depends on question to question and the identities being used. So you need to remember, you need to learn these identities, because you don't get a list or a table of identities in your examination. So yes. Let's discuss another example here. Reducing the Boolean expression a equals to xy plus x whole bracket y plus z plus y into y plus z. So this opens up to this xy. We open the bracket like we do in mathematics. Xy plus xz plus y, we write it as it is, plus yz. So using the idempotent law, y dot y tends to just 1y. So here we get, and again x plus y will also lead to just 1xy. So we get the simplified terms as xy plus xz plus y plus yz. Now here we can take common as y. In bracket we get 1 plus z, and which will again be 1. So we'll get the equation as xy plus xz plus y. Now again we can take y as common, wherein in the bracket we'll get as 1 plus x and plus xz. So 1 plus x will be 1, y dot 1 will be y, and xz remains as it is. So this is what we have simplified this big question into just two terms, which is y plus xz, which can also be represented in the form of gates. Coming to the next method of Boolean simplification, Carnot map or the K-map. In this, we can see the first one is a 2-variable K-map, the second one is a 3-variable K-map, and the third diagrammatic representation is a 4-variable K-map. Note the order, that is why I've highlighted this. This is important because your answers would depend on this order. So additionally, you can also do numbering over here in K-map. Numbering is in a specific way we'll discuss through an example, but I'll tell you here in brief as well how we number. Here is 0, 1, 3, 2, 4, 5, 7, 6, and then we leave this one, third one. We go on to the fourth row. We go on to 1, 0, 1, 2, 3, 4, 5, 7, 6. Here is 8, 9, 11, 12, 13, 14, 16, and 15. Okay, so and here you have your digits 0, 1 in 2-variable, 0, 0, 0, 1, 1, 1, 1, 0, and so on and so forth in this 0, 0, 0, 1, 1, 1, 1, 0, 0, 0, 0, 1, 1, 1, 1, 0, which you can also visualize as a 4-input truth table as well. How do you write the numbers for that? It is similarly noted in the K-map. So in K-maps, we group the given numbers or whatever we are plotting on the K-map, we make it into a group. So it can be a pair, it can be a chord, which means 4 digits in a grouping. Pair would mean 2, and an octet, which would mean 8 digits in a grouping. So here in this example, we can see this is a pair, this is a pair, this is a pair. And in such kind of example, which we are seeing as B, mentioned as even parity function, here no grouping is possible. So these individual ones will be circled as it is. So how do we write the expression for this A? So this pair, if we talk of, here this 1 corresponds to A, this 0 corresponds to A bar, this will be B bar C bar, this will be B bar C, B C, and B C bar. So for this, What we have in common is A, and A is there for sure. We need to check from these two rows, these two columns, what we have in common. 0 1 is different, 1 1 is same, which means C. So the answer to this one, A from here and then C from here. Likewise, we get for this pair A from here, B from the above AB, and likewise for this pair we get B as common and C as common, because here it is A bar and A, it is varying, so we take the column term, which is B, C. For this one individually we have, so this, for this one it is corresponding to A bar, and this is B bar, and this is C. For this it is corresponding to A bar, this is B, this is C bar. For this we have A because here it is 1, and since it is 0 0 here we get B bar, C bar, and for this one we have A, B and C. K-map is basically a 3D map, you can imagine, that when you fold the edges of it, it will come around to a complete structure, like a map. The edges are connected. So we can also form a pair or a chord or a group if the ones are at the edges. Like here we see in this example that these ones and this one we have at corner, so this and this will completely make a chord which is having 4 ones. This is one pair, this is one pair, so in all together we get one chord and 2 pairs. So the expression for this chord, since this is varying, the only thing that is remaining constant here is C bar, right? Here it is 0, here it is 0, and 0 would correspond to C bar. These are changing. For this pair we get the expression as A bar because it is 0 here, and B because B is the only thing which is common here. And in the third pair we get A, since it is 1 here, and the only thing which is common here is 0 0, which is B bar. So these are the groupings further, and the minimal expression depends on the groupings. One thing that we need to remember is that when we are going for logical simplification, Boolean simplification, we should always go for the higher combination, which I mean to say is that if a pair is being made, a chord is being made, or an octet is being made, always go for the higher grouping. For example, we would choose a chord over a pair and an octet over a chord. Yeah. No redundant groupings. Groupings, the ones should not be repeated. Okay. We talked about the K-map, its rules, the groupings, and how do you do the numbering, how do you do the plotting, and how you go for logical simplification, expression derivation. Let us discuss this more clearly for your more clarity with an example in a 4-variable K-map. For example, this question here, we have f of a, b, c, d equals to sigma. So the sigma would would represent SOP, which is sum of product forms. And if there is a pi over here, that will be product of sums. The difference is nothing. The plotting, the solving, the expression remains same. Only difference here comes is that SOP is sum of products. Pi would mean product of sums. So the answer, the way we write, that will change. In this form, sigma, SOP, sum of products. Right? So how we write it? Like A, B plus BC, sum of प्रोडक्ट्स आपस में प्रोडक्ट हो रहा है एंड ओवरऑल आपस में फंक्शन जो हो रहा है वो और का हो रहा है which is addition. So for example here we have to plot values at 0, 2, 5, 7, 8, 10 and 13. See this K map. So this is what I was telling you, how we number it. In green are how we are numbering the K map: 0, 1, 3, 2, 4, 5, 7, 6, 8, 9, 10, 11, 12, 13, 15, 14. Please remember the sequence is very important. It's not like 0, 1, 2, 3. It's 0, 1, 3, 2. It's not 4, 5, 6, 7. It is 4, 5, 7, 6. Again, it's not 8, 9, 10, 11. It's 8, 9, 11, 10 and not in the third row but in the fourth row. And then we fill the third row, which is with 12, 13, 15 and 14. Sequence is important. Now go back to the previous slide. Here we see that we have to plot at 0, 2, 5, 7 8, 10 and 13 and 15. So 0, at 0 we plot 1, at 2 we plot 1, at 5 we plot 1, at 7 we plot 1, at 13 we plot 1, at 15 we plot 1, at 10 and at 8. So this is given in your question. 0, 2, 5, 7, 8, 10, 13 and 15. We plot 1s here, and now we see what groupings can be done. A chord, an octet or a pair. So here we see, first of all, it is striking that in the center that we get a combination of 4 ones which will make a chord here. And since I mentioned earlier that K-map is a 3D figure, so if you fold the edges, it will come as one, like you imagine a map. A map is spread out, but as you fold it, it's like a globe. It's connected. So this K-map also folded will get connected. So the ones at the corner will be connected once this K-map is folded. So that is also one grouping. So individually we see how at the 4 corners these ones are grouped into a chord. So here we get the expression, it's PQ and RS, and the numbers are plotted as it is, 0, 0, 0, 1, 1, 1, 1, 0, like we discussed, and likewise here in latitude and longitude. In the red chord, we get expression as QS. Why QS? Because here Q is common, because this is changing. P here is 0, P here is 1. So that is changing, but Q is constant. So Q, one term. And then we see in the column what is common. R is changing here. R is 0, here R is 1. The constant thing is S, so S is 1. So the answer is QS for the red chord. For the purple chord, we have to see again what is common. It is Q bar from here, and it is S bar from here, because here S is 0, here S is 0, so S bar. Again here Q is 0 for this, so it is Q bar. So the answer to the purple chord is Q bar, S bar. To the red chord, it is QS. So this is how we simplify our Boolean expression from a K-map. I hope this gave you somewhat clarity. Coming to our last topic of discussion for this digital electronics series is the topic of memories. So the memory devices are digital systems that store data either temporarily or for a long term. Digital computers to hard disks have built-in memory devices that can store the data of users or manufacturers. Memories are made up of registers. Each register in the memory is one storage location. Storage location is also called a memory location. Memory locations are identified using address. And the total number of bits a memory can store is its capacity, and a storage element is called a cell. Types of computer memory. Talking of the types of computer memory, we come to cache memory, which is a temporary storage area known as a cache. It is more readily available to the processor than the computer's main memory source. It is also called CPU memory, which is the central processing unit memory, because it is integrated directly into the CPU chip. Then we come to the other classification, which is RAM and ROM. And further, RAM has another classification. RAM is nothing but random access memory. It is one of the parts of the main memory, also famously known as the read-write memory. And as the name suggests, you can read as well as write from the memory. Random access memory is the memory which is present on the motherboard, and computer's data is temporarily stored in RAM. It can both read and write. Further classifications of RAM are DRAM and SRAM, which is dynamic random access memory and static random access memory. Dynamic RAM uses capacitors and transistors and stores the data as a charge on capacitors. They contain thousands of memory cells, and it needs refreshing of charge on capacitor after a few milliseconds. This memory is slower than the static RAM. Static RAM uses transistors, and circuits of this memory are capable of retaining their state as long as the power is applied. So this memory consists of flip-flops, with each flip-flop storing one bit. So you get the difference how we are progressing from a static memory to a dynamic memory, then we're going forward to the ROM. It has less access time, and hence RAM, static RAM, is faster. Read-only memory is a non-volatile memory. Non-volatile and volatile, there are two types of memory. So volatile is basically when you switch off your power supply, all the data goes. But in non-volatile, even if you switch off the power supply, the data is not erased. So ROM is a non-volatile memory which is used to store important information used to operate the system. We can only read the programs and data stored on it. We cannot modify or delete it. So the masked ROM is the next classification, which is hardwired devices with a pre-programmed collection of data or instructions were the first ROMs. Masked ROMs are a type of low-cost ROM that works in this way. We come to the next classification of memory, which is programmable read-only memory, PROM. This read-only memory is modifiable only once by the user. Its content can't be erased once written. So there's no option of erasing the memory once the contents are erased. So we came on to the next advancement. What is the drawback of this? That you can't erase what is once written. What do you want? That you could possibly erase it once or maybe more. So then, because memory is one of the precious things, you cannot just get over with it and then purchase more memory. So you need to save onto that. So if once the data is done, used, you can again rewrite it. So that came with EEPROM, which is erasable programmable read-only memory. EEPROM is an extension to PROM where you can erase the content of ROM by exposing it to ultraviolet rays for nearly 40 minutes. Then we come to E-square PROM, which is electrically erasable programmable read-only memory. Here, the written contents can be erased electrically. You can delete and reprogram E-square PROM or EEPROM up to 10,000 times. Erasing and programming takes a very little time, which is nearly 4 to 10 milliseconds, and any area in E-square PROM can be wiped and programmed selectively. Coming to the other classification, which is primary memory and secondary memory. So primary memory is also referred to as the main memory or the internal memory. It is a computer system's temporary storage component which is directly accessible by the central processing unit. It houses data for immediate processing. The characteristics are volatile, that is, data is lost upon power loss, high speed access, limited capacity relative to secondary storage, and the examples are RAM, ROM, cache memory. The advantages are high speed access, data can be retrieved and stored very quickly, directly accessible by CPU, so the no intermediate steps are required for data transfer. The disadvantages are volatile, that data is lost when power is turned off, limited storage capacity compared to secondary storage, primary memory is relatively small, it is expensive because cost per unit is higher than secondary storage. And the different applications of primary memory are temporary storage, multitasking, buffering, caching. Secondary memory or external memory serves as long-term storage for data and programs. Unlike primary memory, it is not directly accessible by CPU, it requires input-output operation. It is non-volatile, that data persists even when the system is powered off, slower access speeds compared to primary memory, high storage capacity. Examples are hard disk drives, solid-state drives, optical drives, CD, DVD, Blu-ray. It is non-volatile, it has large storage capacity, can store vast amount of data. It is relatively inexpensive for cost effective for storing large volumes of data. Whereas the disadvantage is slower access time because the data retrieval is slow as compared to the primary memory. It requires input-output operations because data transfer involves additional steps. So this is it for the discussion on digital electronics, wherein we discussed the basic gates, their truth tables, their symbols. Then we talked about universal gates, NAND NOR gate, how you can construct the basic gates using the universal gates. Then we proceeded with Boolean algebra, discussing the various identities of Boolean algebra and how we use those identities to solve a question for Boolean simplification. Then we went on to discuss about the Karnaugh map or the K-map and how we plot the K-map in SOP form, in POS form, how we solve the expressions, and how we get a simplified output for a given input. And then we discussed about memories and the various types of memories like primary memory, secondary memory, RAM, ROM, static RAM, dynamic RAM, PROM, programmable read only memory, erasable programmable read memory, electrically erasable programmable memory, cache memory, so on and so forth. So I hope you had a good learning session, and you need to revise your concepts so that we can discuss furthermore topics of digital electronics and furthermore questions for solving with Boolean algebra, with K-map questions. Happy learning. Go on. Best wishes.